Hello, and welcome to Earth Science Chapter 2 lecture. In this lecture, we're going to learn about minerals. Minerals are essentially the building blocks of a lot of what we're going to talk about in the class this semester. So we've got Chapter 2, which is about minerals, and we'll look also in the lab 1 is all about minerals. So we'll get to see and feel and perform some chemical analysis on a lot of different types of minerals. So minerals, we just kind of think about what is a mineral. It is something that is naturally occurring. So minerals are formed through natural geologic processes. They are inorganic. Inorganic means that they don't contain long carbon chains, so their building blocks are not made up of what we call hydrocarbons. So minerals are generally inorganic. Things like calcium carbonate, sodium chloride or salt. These are examples of inorganic compounds. They are solid. Only solid crystalline structures can be considered to be minerals. And when we talk about this crystalline structure, they are orderly. So they are made up of atoms that are arranged in a definite orderly pattern. And then they have a definite chemical composition. Most minerals have a chemical composition that can be expressed using a chemical formula. For example, quartz is a mineral and it has the formula SiO2. It is silicon dioxide is what quartz is. Some minerals have some variations, but they can only be variable within definite specific limits. In Chapter 3, we'll talk about rocks. Rocks are naturally occurring and they are solid masses of mineral or mineral-like matter. They are aggregates, meaning that there can be several different types of minerals that are not in a definite composition. So here we have an example of granite, which is a rock, and it is an aggregate. It is a collection of several different types of minerals. And you see in this particular one, we have some quartz, we have hornblende, and we have feldspar. So those are the minerals, and you can see that there's not a specific pattern, there's not a specific arrangement of those minerals within the rock. The next section in Chapter 2 goes over a little bit about chemistry, some kind of foundational knowledge about chemistry and bonding. And I'm going to skip through that because that will be a review. If you need a little refresher on that, go ahead and feel free to review that. But I'm going to skip on over to section 2.4 and look at the properties of minerals. Minerals, when we look at their properties, and this is what we're going to observe in the lab this week, we can classify minerals based on their properties. We know that they have definite crystalline structures, they have chemical compositions, and because of that, they're going to have unique physical and chemical properties. So we can use tests to demonstrate these properties so that we can determine or we can classify minerals. Some mineral properties are called diagnostic properties, and these are those that I was talking about that we can used to actually identify a particular mineral. Some properties are called ambiguous properties, something like color. Color can vary between samples of the same mineral, so we can't use color as a diagnostic property. It has to be, or it's considered an ambiguous property. So here we have the optical properties of minerals, and you see this is luster, color, streak, and ability to transmit light. So when we talk about optical characteristics or optical properties, these are things that we can observe with the naked eye. Oops. So luster, does it reflect light? Okay. On page 40 in your text, you can see two examples of galena, a broken sample of galena so that we're seeing the inside of it, and it has this metallic luster. It reflects light, it looks kind of metallic, but then you see a piece of galena that's tarnished, that's not been broken so that we can see the inside of it, and you see that it doesn't have luster. Okay. So minerals that are shiny, like this metal, are said to have a metallic luster. Those that have a non-metallic luster can be described using words like dull or earthy, vitreous. Okay. Color, something that's easily observed, easily seen, but is considered an ambiguous properties. It's only considered a diagnostic property of very few, and we'll look at a couple of those in the lab. And then we'll look at streak in the lab. We have these plates which are made of porcelain, and we take the mineral and basically use it to draw a line on that plate, and the color of the mark that it leaves can help us diagnose or help us identify the particular type of mineral that it could be. Now, not all minerals leave a streak, and that can also be a diagnostic property. And then something else that we look at is the ability to transmit light. If light passes through the mineral, we can describe it as being translucent or transparent. If it does not transmit light, we say that it is opaque. Then we can look at the shape of a crystal. So again, minerals have these crystalline structures, and so we can use the crystal shape or habit to look at the common or characteristic shape of individual crystals or aggregates of crystals. So some minerals tend to grow equally in all three dimensions, but others can be flattened or elongated in one dimension if they can't grow in another. Some crystalline minerals have a regular shape that helps us identify it. And your book gives some examples. Magnetite crystals occur as octahedrons. Garnets form dodecahedrons. Halite and fluorite tend to grow as cubes or very near cubes. Most minerals have just one common shape. Others can have a few. And there's an example of pyrite on page 41. It has a couple of different shapes. Sometimes a mineral sample will consist of intergrown crystals, and you can see some of those here on the screen. We can have fibrous, bladed, tabular, or like a table. Cubic would be like a cube, prismatic, platy, blocky, or banded. And we'll look at some examples of these in the lab. Then we can look at mineral strength. How easily they break or deformed is determined by the bonds that are holding those different atoms together. Hardness is a measure of the mineral's ability to resist scratching or abrasion, and this is determined by what we refer to as Mohs scale, M-O-H-S, Mohs scale. And this is a scale that runs from 1 to 10, 1 being the softest and 10 being the hardest. It is a relative ranking. So we see diamond is classified as the hardest, talc is the softest, and these on this list are considered to be our index minerals. So we're basically saying, is something harder than talc, but softer than calcite, then it could be a gypsum. Okay, gypsum has about a 2. So we can compare the hardness. And so we have another plate that we use to help us determine hardness scales. And you can see some other things too, like we can use a street plate, we can use a penny, we can use a fingernail. Talc and gypsum can both be scratched with just your fingernail because they're so soft. Another thing that we can look at is cleavage, and this is the tendency to break or cleave along planes of weak bonding. Not all minerals will exhibit cleavage, but some do, and they can be used to identify them. So if we look at muscovite, for example, muscovite basically kind of flakes off. And so it has cleavage in one direction. It's almost like these little sheets that are laying on top of one another. And muscovite is an example of what's called a mica. And all micas have this cleavage in one direction to form these thin, flat sheets. You can see some other examples here. Cleavage in 2 directions at 90-degree angles. And basically this is the area in which they break. You've got feldspar with the cleavage in 2 directions at 90 angles. You've got hornblende, and you can kind of see the cleavage there. And when we talk about cleavage, so if you look at where they've got the surfaces labeled 1 and 2, what we're looking at here is that the stripes or the lines, the patterns in the mineral are consistent on both sides here, and they form this almost perfect 90-degree angle. And so this is considered cleavage. Okay, down here is a fractured rock. You can see that they're not all running, the pattern is not going in the same direction. So this is considered to be a fracture, not a cleavage. Now here, we've kind of got the same situation. We've got the same pattern in the top and the side, but we don't have a 90-degree angle. We've got this bigger angle here. So this is still cleavage in 2 directions, but we have an angle that's not quite 90 degrees. And then something like halite can have cleavage in 3 directions at 90-degree angles. And again, you just have to look at the pattern in your mineral. Calcite, notice it's also a cube, but it's not this kind of perfect shaped cube. The cube angles are less than 90 degrees. And then fluorite can have cleavage in 4 directions. This fluorite forms like a diamond shape, or what we consider, a rhombus or a diamond shape because of its cleavage. Okay, so fracture is breaking, okay, and it's breaking in a random pattern. So cleavage is still breaking, but it's breaking along the plane of bonding. Fracture is just a brokenness, okay. Tenacity is how well the mineral responds to stress. whether it tends to break or bend. Things like gold or copper tend to bend instead of breaking, and so that can be some characteristics that we can use as well. Density is the mass per unit volume. And in terms of mineral, we use something called specific gravity to represent the density of minerals. And this is a ratio of the mineral's weight to the weight of an equal volume of water. And basically, we kind of relate this, to something being dense. So if we have this tiny mineral, but it feels really heavy for its size, then we would say that it has a high specific gravity. Quartz has a specific gravity of 2.65. Galena, when you pick up a sample of galena, it is really heavy for its size. So it has a specific gravity of about 7.5. So its specific gravity is a lot higher. Now, some other properties of minerals, taste. Something like halite is just salt. It's where salt comes from in salt mines, and so you can lick it and it tastes salty. We're not going to do that in the lab, but you could. Talc feels soapy. It's like you can't get it off your hands. Graphite feels greasy. If it contains sulfur, it has a distinct sulfur smell. Some are magnetized. They can be used to pick up, paper clips and nails. Some are, have elasticity, meaning they can kind of stretch. Some are malleable, meaning they can be hammered into a sheet. And then one that we're going to do in the lab is the reaction with hydrochloric acid. This is used for detecting our carbonate minerals. If we place a couple of drops of hydrochloric acid onto the mineral, samples that contain carbonate will kind of bubble or fizz. The next section here looks at what elements, so when we talk about elements, we're talking about, elements from the periodic table. These elements that compose the rock-forming minerals. So we have these 8: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium compose the majority of our rock-forming minerals. And so you can see here their relationship, how much is found in the Earth's crust, which is where our minerals and rocks come from. So the silicate minerals are the most common, and they contain what we call a silicon-hydrogen tetrahedron, and this is shown for you at the top of page 45 in your textbook. They kind of make this almost pyramid type shape when they bond together, and they are arranged in groups based upon how those tetrahedra bond together. And here is a table kind of showing you some of those more common silicate minerals and what those bonds with those tetrahedra look like. So at this point, I'm going to stop sharing and then come back with our smart figure and watch this little video.
This is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the relative importance and basic structural similarities of the most common group of minerals in the Earth's crust, the silicate minerals. If you look at this image, you'll see a rock that's actually one of the most common rocks in Earth. This is peridotite. It's an igneous rock that's very common in the Earth's mantle. It's made out of a mineral called olivine, mostly, with a little bit of the mineral pyroxene in it as well. Both of these minerals are silicate minerals, and so silicate minerals make up a huge portion of the mantle. They also make up a huge portion of the crust. Here's a pie chart showing the relative proportions of different elements in the crust. I'm not going to go into this in a lot of detail, but what I want to call your attention to is that the two most common elements in Earth's crust are silicon at around 28% and oxygen at around 47%. You can see that other important elements are aluminum and calcium and so on. But the key thing here is that a huge proportion of the Earth's crust is made out of either silicon or oxygen. And so you would expect minerals that are rich in silicon and oxygen to be very common minerals. Well, you'd be right. The silicate minerals, the ones that have silicon and oxygen in their chemical structure, make up about 92% of the Earth's crust. Non-silicate minerals, in contrast, make up only about 8% of the crust. If we take a look at some of the details there, we see that about half of all minerals in the crust are feldspars of one kind or another, either plagioclase feldspar or potassium feldspar. Other important silicate minerals include quartz, pyroxenes, amphiboles, micas, clays, and a grab bag of other silicates. All silicate minerals have something in common, and that is that they have silica in them. So in general, the chemical formula is SiO2 for silica. What's shown here in these images are SiO4. The reason for that is we're showing the silicon-oxygen tetrahedron. And this is a really key structure in all silicates, whether or not they have lots of oxygen or relatively little oxygen. So you can see here that basically you've got a silicon atom shown in blue surrounded by oxygen atoms, which are the big red atoms. A more expanded view is shown over here on the right, where you can see the silicon atom in the middle, and then it's bonded to these neighboring oxygen atoms, 4 of them in every direction. Those 4 atoms end up defining a 4-sided face around that central silicon atom, and so it basically is like a little pyramid or a 4-sided figure, a tetrahedron. The plural of tetrahedron is tetrahedra. Those tetrahedra can be linked to one another in various ways. So some of those ways are illustrated here. You can see that they can be independent tetrahedra. The tetrahedra can be linked together in single chains. The tetrahedra can be linked together in double chains. The tetrahedra can be linked together in big sheet-like structures, or it can be more complicated. Let's take a look first at the independent tetrahedron situation, where you've got these little tetrahedra bonded to other atoms, and these atoms are usually positive ions like magnesium or iron. And this is the case with that green, the peridotite, that mineral that makes up most of the peridotite, olivine, is made out of a crystal structure that looks something like this. So that's up here at the top, olivine. You'll see that our single chain silicates are called pyroxenes. Augite is a specific example of a single chain silicate. The double chain silicates are members of the amphibole group. Hornblende is our example mineral there. The sheet silicates are biotite and muscovite. They're both examples of micas. We've seen micas in another smart figure where we talked about mineral cleavage. And then lastly, we've got the more complex 3-dimensional networks. And basically these are in 2 main groups, the feldspars and then quartz. The feldspars are the most common minerals in the Earth's crust. So they occupy together, potassium feldspar and plagioclase feldspar, we're talking about half of the volume of the crust. It's a tremendous volume of the crust. And they come in many different varieties. Some are richer in potassium, some are richer in calcium, some are richer in sodium, but we end up seeing that these minerals are very, very common in Earth's crust. Okay, let's see how much you remember. Here's a hornblende and an augite. What's the silicate structure of these minerals? Remember that hornblende is an example of an amphibole, and augite is an example of a pyroxene. Hopefully what you said is that hornblende is an example of a double-chained silicate structure, while augite is an example of a single-chain silicate structure. Okay, thanks very much for your attention. This concludes another Smart Figure. This is Callan Bentley. Welcome.
Okay, so there you could see an example of some of those minerals, those silicate minerals, and we will go through those in our lab this week as we look at our different minerals. Some of our other minerals that we have, I'm going to skip through the silicates here. Some of our non-silicate minerals you see listed here, and we can see these in the book on page 49. So we have our carbonates. Carbonates are primarily composed of calcium carbonate. We have, and you see the examples there of calcite and dolomite. They're usually found together in limestone and dolostone. Limestone is used in like gravel and also as a building stone. It can be found in a particular type of cement called Portland cement. Then we have a couple of others. The halides and gypsum are very common in sedimentary rocks. They are basically the remnants of seas that have evaporated and left behind chloride and fluoride. We have things like hematite and magnetite that contain iron. Magnetite, you see there it's got some paper clips stuck to it because it is magnetic. We have the sulfides, things like galena, which contain a lot of lead, and this is where lead comes from. Sphalerite contains zinc. Chalcopyrite contains copper. Cinnabar is where we get mercury from. So these sulfides are important in mining because this is where we get some of these metal ores from. We have sulfates, and then we have just our native elements, our single elements, things like sulfur, silver, copper, gold. So minerals are considered a non-renewable resource because we have fixed quantities, and yes, they can be replenished, but it takes millions and millions and millions of years for that to take place. So mineral resources are basically where we can find useful minerals that can be extracted. And so, like I mentioned, those deposits of ores, very important in mining those minerals. So here's an example of a copper mine in Utah. And the amount of copper that's found there is less than 0.5%. But because there's so much that's removed every day from it, we're able to get large amounts of copper. And we also have found in this particular mine, in addition to copper, gold, silver, and molybdenum. So it is, when we talk about minerals and we talk about mining for ores, a lot of those ores are locked up in, these other minerals. And so we have to mine them from the rocks and minerals that are on the Earth's surface, and then actually extract out the ore that is needed. So hopefully this has helped to summarize Chapter 2 about the minerals, and we will, I think, when we get to the lab this week and you are putting your hands on these minerals and doing these, tests with the minerals, then I think that you'll really be able to understand some of these properties a little bit better. Sorry, I'm trying to share my video. There we go. So that you're not just staring at a blank screen. So I think when you read about it in the book, and even if you watch those smart figures, it's more difficult to really understand all of those concepts and all of those properties. But once you're in the lab and we are, putting the hydrochloric acid on there, we're doing those street plate tests and the scratch tests, and you're seeing the different colors and patterns and cleavage of the different minerals, I think it will help you put all of that together. Now, you don't have to memorize any of the minerals. It's just important that you have this base foundation, because when we get into the unit on geologic processes, we talk a lot about these different minerals and these different rocks and the properties that they have that are going to affect the geologic processes that we're going to observe. Things like weathering and erosion, for example. So it's important just to have a good foundational knowledge of rocks and minerals. Thank you for watching.